Hello.
All right, we're having lecture number 2, and this is our recorded lecture associated with Introduction to Robotics. We will start out by looking at lab number 0 videos. So what better way to start the day than to play videos? Some of these some of these you'll look at and you'll say, wow, they've certainly got a lot of time on their hands. Some of them are so short, I have no idea what the robot did. So I'm going to ask you a question. So let's start out. For those of you who are viewing this in video land, this is on my class webpage.
Oh, they're putting on
Fire.
This is dark. Is there any reason for that? Or? Okay. So when it's dark, it stops, and I'm supposed to see that it stops. Can you see that stop? Yeah. Okay. Probably should have had infrared camera. The sensors used are obviously audio for fire. What else are you using?
Light sensor.
Light sensor and?
Sonic.
Sonic for distance. All right. What do you think? Is that cool? You think a middle school kid would like that?
Yeah.
Oh yeah, something that fires. All right, there we go. So let's look at the next one.
Oh, I was gonna suck. I didn't play music or anything.
Now everybody's kind of like, oh man, mine's gonna suck compared to that one. All right, here we go.
Which one is ours?
Like the fifth one.
Yeah.
They did use the whole box.
Go.
Any hint of what it's doing?
Except the wall and turn around.
All right. It said ouch, all right? So obviously it is a bump sensor. It started out with audio, right?
Yeah.
So it's a sound sensor. And then is it using obviously the ultrasound? It says ouch again. All right. Let's see. By the way, I went through and I think I liked every single one of them. So now you have some likes on your videos. I'm sure that's
the
pretty
YouTube video.
fun.
You know, that I put the 2 links, right? One of them is on like that.
Like what?
After he
Now is this in one of the downstairs classrooms?
Yeah.
We used
Whoa.
Now you're pushing the
Awesome. That's cool.
Oh my god. It's kind of low battery, so you didn't.
Yeah, it's supposed to go
Oh,
faster.
okay.
But it
So
kind
it's
of
not in the wall.
gets into defense mechanism.
Yeah.
Defense mechanism.
And then
Okay, so what sensors are supposed to?
It's just
When it sends a wall, it kind of stand up a little.
Ah, I see. Okay.
Yeah.
When it senses a wall, it stands up.
kind of like fight mode.
Fight mode. Okay. All right. I can do that.
The robot drinking. The first place.
All right. I'll close off some of these because otherwise I'm going to have to go all day.
It's made because
All right.
For this project, we use the microphone, the ultrasonic sensor, the light sensor, and the touch sensor. Each one will be demonstrated separately, beginning with this microphone.
By the way, I like this one.
Next, the touch sensor. Once it finds a line, it will use the light sensor to follow it. Using the ultrasonic sensor, we will detect the obstacles in its path. It will then circumvent these obstacles, be able to recheck and see if it's still in its path. And pass the obstacle, and then find the line again. And continue following it. You can also stop on a sound, and then begin again.
What the heck are you banging?
Stopping.
Probably can make it.
Oh, no, I'm trying to make it longer.
So that one I liked. By the way, I have no idea why this shows up. That shows up after the video. Why is that?
Play it.
I don't dare play that one. I know that's just trouble. That's just trouble for me.
Robot anatomy.
Alrighty. Now this is interesting, although De Los Santos and Salazar.
Yes.
One thing I should recommend to you, you can actually, using YouTube video editor, you can have it rotate the video, which might have been helpful for this first one.
I think we showed that last video.
I tried
School
to-
children, I think would be.
I tried to look for it, but I tried to look for it. I mean, the real video, it's landscape. I don't know.
Robots on a wall.
Yeah, it's a spider robot.
Alright, so it's doing line following, but it's also using the ultrasound to look for an object,
Yes.
like this. And I tell you what, that's cool for kids to see, right?
Yeah.
Actually, it laughed afterwards.
That's the one that. That's the one they.
And the amazing thing is that the box has legs, and it just moves away.
Oh man. What was
I like your title card there. That's
How'd you
really
guys
good.
make it turn around like that?
Just put a sensor.
Always goes on a little. Turn around.
So yeah, in the future it might be helpful if you you can rotate the video using the editor, but that's a pretty good effort. I like that. But you know what? In case you didn't see it good enough, you gave me 2 videos.
Yeah,
Take 2.
The volume is not good.
that would.
I just want to see it smash again. Yeah.
I want to see what comes off it.
It's like a guy, man.
Oh, is it?
What?
That's awesome. That
So obviously you enjoyed finding the sounds for these, even though it wasn't a requirement.
I know.
And actually I've heard several sounds. And use sound to start and stop?
No, well, to start,
To
no,
stop.
but to stop the robot.
Start automatically.
Okay.
Just stop.
Alright, here we go.
So?
Alright, I have to admit, I have no idea what this thing is doing.
Well, it was supposed to scan around, look for the
People?
object within like 30 feet or something, and then move toward it, and then stop when it's like 10 inches away.
Okay, so it's looking for something within how many feet, with which range?
30 inches.
30 inches, okay. So, you've got very nice socks, by the way. All right, so obviously obviously this uses ultrasound. What's the other two sensors it uses?
Well, I was going to use the touch one, but then it stopped before it touched it, so it couldn't stop it.
Ah, there's a trick to that. Use one of the big long sticks. One of the big long sticks will actually go into the sensor. All right, I think we saw this. It does the same thing again and again. All righty. Okay. Well, I'm not all that sure about what it does, so let's go back over that. Is there a slow motion?
I don't know.
All right. So I detect there's something like it's light following.
That's me. No, it's actually a light sensor, so it stops when it sees bright light.
Okay.
And we were limited by, this is our camera here,
We could
so
only put up so much.
7 seconds was like the limit I could email to myself. Yeah.
So we kind of had to make it go as quick as possible.
We had a much more detailed video, which we can show at a later date if you're interested. But,
I do want to point something out here.
That's like 2008.
What do you see here that you didn't see with the naked eye?
The what?
It's right here
Yeah.
is an infrared light,
Yeah.
which you can pick up with cameras, cell phone cameras and other cameras, but you can't see.
I actually saw that on ours when we did it.
You can
It's just a red
barely
light
see it,
that
but you can
turns
see it
on.
really good with a digital camera.
Yeah. All right, and what other sensors did it use?
ultrasonic, and then the back's got a little bumper on the back, so when it hits the wall, it goes back in the direction.
And then right there, we put like a piece of paper or something in front of
Yeah,
it.
you can
and
see the
it
shadow.
runs backwards.
Ah, okay. Do I need to take your, do I need to take your, do I have to trust you on that one?
Yeah.
Yeah, okay.
Yeah. We're up for an Oscar. Take it to the bench.
Why so fancy?
Yeah.
Wow.
Not good. Probably bad.
person.
Yeah.
Robotics for UNC Charlotte, summer session 1 of 2012. This is Lab 0, Lego Mindstorm. This is the Stalker 1.0. It's capable of finding moving objects, following that person or object at a safe distance, and retreating when too close.
Stalker.
The robot is activated by a clap.
Obviously, it's looking for the person who's taking the picture, and it's not getting too close. Now it's coming closer. So it's keeping how much distance?
I think it was, it can detect 15 inches. Yeah.
15?
50 inches.
50 inches, okay.
Close, close, close.
That all. Nice little video stuff as well. What was this done with, by the way?
Windows Movie Maker.
Windows Movie Maker, so the freebie.
Yep.
Wow. Okay.
I have the software.
I got into that. Make all those pornos.
I just didn't want to use like 20 spirits.
What the fuck?
It is the Terminator.
Terminator?
What does the Terminator do? Oh, it fires! Alright. Well, the thing I realize is obviously you guys didn't get these firing things in your kits, did you?
No.
We didn't get that.
So what is that from?
Oh, that was actually rubber bands. We have half the robot here today. The other half I left at my farm because I didn't get it wanted it wet.
Okay, so this Terminator does what with the 3 sensors?
2 of the sensors are actually same, but they're the infrared, not infrared, yeah. Ultrasonic.
Ultrasonic. You have 2 ultrasonics?
Yeah, one from the kit he had and one from my kit. That
Ah, okay. Well, here's a good example or a question. Can you use two ultrasonics?
Yes.
What do you have to watch out for?
Make sure I
But
don't.
they don't conflict.
Because think about this, if you're writing software that's pinging both ultrasonics at the same time and receiving them,
We actually had two separate brains for it.
okay, oh, two separate brains, okay. Well, it still is the same case.
Sure.
One ultrasonic signal can be picked up by the other ultrasonic sensor, unless they're different frequencies. But in the case of our cheap little, cheap, I mean, our Legos, they are relatively, or they are the same frequency, and they don't make different ones. They do make, if you buy off-the-shelf ultrasonic sensors, they will have ones that differ by about 5 kilohertz, I think is the most I've seen.
Yeah. The lower part was supposed to just kind of see if there's a person in front of it. If you just kind of pass in front of it, it just stop, then move again. And otherwise it'll just kind of turn, check right. If there's nothing there, go for it. If not, turn left and go the other way.
Okay. And it fires something at it. Okay.
Yes.
All right, and this, obviously it's using the light sensor to follow it. What other sensor?
Sound.
Sound
It
to start?
starts. It starts when you couldn't really hear it there, but it started when it hit the wall, and then it follows the line, and then when it hits something, it stops and goes the other way, and then the ultrasonic just stop within 6 inches.
So you used 4 sensors.
Yeah, but I only put. I think I named it like robot 3 sensors or something, but
Okay.
yeah.
But you used 4. Ooh. Okay. We have a high achiever over here. All right. And
Oh, really? It's okay.
oh shit.
Car ramrods, really?
Car ramrod. This box is a touch sensor, a sound, and sonar to detect the distance from the target and when to attack. This is how it works.
Stick 'em.
All right. That was all rather interesting, wasn't it? All right. So. The question which comes to mind is, why did I have you do this? Why did we work?
Why play with Legos?
All right, play with Legos. Any ideas?
Familiarize ourselves with the basic fundamentals of robotics and robotic systems. Corey, I work there.
That's how you roll.
I take robotics for 400.
All right, and systems. I like that. Any others?
Teamwork.
Teamwork.
Not really.
Well,
Any others?
to have fun.
Ooh, have fun. Did you learn anything?
Learn G programming.
Told me to write.
Ooh.
Programming, you don't make languages.
Graphical programming.
That's what that was?
Yes.
All right, are you being serious or are you?
I mean, I knew the type of program, but I didn't know it was like a legit type of programming.
So,
That's how
how many of
Labview
you
works.
have used Labview before? All right. How close was this to Labview?
Really
Annoying and simple.
This is a lot simpler than LabView, right?
Way more limited.
Stripped down version of Labview.
All right. This is LabView.
Yeah.
The programming interface is powered by LabView behind. They kind of dumbed it down a little bit to make it a little bit simpler, but this is LabView. And in fact, if I were nuts enough, maybe I should do this. Should I make another lab in there just for grins?
No.
No? No?
A better light
Well, I'm thinking they come up with, or there is a LabView interface for programming these Legos. In our lab, we have, you just run LabView, and you're able to program these things. Should we do that? What do you mean? You're shaking your head. Don't you want a nice, easy way to do the same thing you just did with this Lego robot?
What do you mean, nice, easy way? This was so easy.
I don't think you beat the Lego in NXT.
Well,
Yeah, what's going on?
I took it
I
apart.
think they got the market.
Programming used like 5 things that you just moved over.
but this might be, you know what, I might just change my mind. Yeah.
And do the
yeah.
same lab again, but recreated it.
So lab number 1 is to, are they still running out there, I hope? You didn't change anything out there, right? Okay. So I'm changing things up. Why not? It's fun. Lab number 1 will be to do the same thing you did with LabView, which means that you're going to need to use our machines in 203. All right, here we have all the questions. Yes, sir.
Same bot or new one?
If you want to do a different one, that's fine. But I want you to do the same concept. Oh, you saw something else you liked better, right?
No.
Once improved, it still works.
Or you can improve it. But you need to use the LabView interface. You need to do screenshots. And for this one, you're going to have to do a demonstration in addition to, no, instead of a video. You need to do a demonstration. You have a question up here first.
When is this going to be due?
1 week from today. Yes.
Will we be able to access the LabView from Mosaic online?
Will you be able to access LabView from Mosaic?
Online.
Online. The answer is no. There is a LabView online, but it doesn't have the plugins to actually program a Lego Mindstorm. So this might require you to do some playing. Now keep in mind, you can do the design. I'm thinking. How many of you have LabView on your own PCs? 1, 2, 3?
It only works on
Do
Linux.
you have a license for adding Linux?
Do we have the license for adding it?
It only works on Linux?
You could just do a toolkit, I guess. Probably be a toolkit probably.
What you need to do is you need to have, I wish I had Adam here because he did that. Did you do it too as well? Did you load it? Yeah, we'll look at the details in a few minutes, or during a break, not on screen. But if you have LabView, there's a simple plugin for running LabView, but programming your Lego Mindstorms. So that means that if you have a copy of LabView, I think the student version of it is inexpensive. We actually also have a couple of laptops we might loan out. I'll have to look to see if we still have them around with it loaded. Question up there first? Yes.
Yeah. With LabView, is there like some way of using ifs and statements like that, and breaks and switches and stuff like that?
Is there a way to use switches and breaks in LabView? Yes.
So it's it should be a lot easier than Lego Mindstorms. Because we were having trouble with our loops.
Yeah.
Like, the loops are really hard to get out of. It's like if you want to write like an if-then statement, it's really difficult.
You can do loops and ifs.
Instead of like, you can't expand stuff out. You can only go like.
It really wasn't that hard to make this. You just have to
No.
I tell you what.
The loops. If you make the loop around like a touch sensor or something like that, it does loop on.
You can also just change the settings on the loop to actually be so that if you set something to be like this setting, then it'll continue to do what's inside the loop. If you break that setting, it'll go out of it.
All right. So I tell you what. This is probably something better shown than described. right?
Yes.
So we'll save some time at the end, and maybe we'll tromps up to the lab and take a look at how to do it really quick. How about that?
Sounds good.
All right, we'll save some time at the end. Question over there.
Oh, I didn't know if we used it in the instrumentation lab in Duke, and I didn't know if there were actual computers that had it here, and if we could maybe get access to that space.
As I said, room 203, everybody will have access to as of tomorrow, and you can go in there anytime you want. And of course, you have these buckets that you can take in at any time. All right. Any other questions? All right. So the other thing I wanted you to think about is when you were doing graphical programming, was it easy, difficult?
No.
Just
Easy.
different, right?
Yeah.
Differently easy.
Way better than C++.
So
Or
way
Java.
better than C++, huh?
Or Java.
Some things were a lot more difficult to actually do that would have been so much easier in a coding language though.
All right, so the main thing I want to point out is that this is a graphical programming interface. It's something that's new for pretty much everybody here. Even the guys in mechanical who used it for instrumentation probably didn't do all that much with it, right?
We used it for like, I think like 8 of the 10 labs.
Yeah.
So-
But you gathered data, did you control anything?
Oh yeah, we did PID motor control.
Okay, so you did control as well.
Um,
Okay, so there's your experts over there. Good thing you guys are spread out across all the other groups, right? I would like to do the following. Well, here's a question for you. Same groups or different ones? All right, who votes same? Raise your hand. All right, it looks unanimous except for the ones that had a divorce, okay? Sorry, guys. All right, so we'll have the same groups. Again, this will be a good, slow introduction to Labview. There are tutorials out there which we'll post more information about, but this will be a good exercise for you to take a look at. So, if we continue on, so we obviously have said that Lab 0 was our Legos, but Lab 1 is going to be Lego and Labview. Which means that our lab number 2 is going to be a Labview and Danny intro. Danny meaning it's going to be the the metal robot that I showed earlier that has the 2 wheels on the front and the Swedish wheel on the back. So it'll be a nice slow introduction for all the work. And then labs 3, 4, and 5 will be more difficult Labview.
Yeah, but that's white. It's not professional.
Don't talk.
Exercises which will be distributed approximately every 3 or every 4 class times. So, without further ado, let's continue on. So, let's just talk about locomotion. So let's look at one example.
I'm Steve Center, Vice President of the Environmental Business Development Office. This has been a really big week for American Honda. It's been a really big week for American Honda and Fit EV as we kick off the electric vehicle demonstration program.
Okay.
Oh, interesting.
I'm Ross Trevor. I'm a technical program manager here at Google. I work on electric transportation initiatives. Our G-Bus shuttle system actually brings in approximately 30% of our workforce to the Labview campus every day. And one of the real perks for being an alternative commuter is you get to use the G Fleet car sharing here.
You know what? This is not the video that I thought it was. Oh, you know what? They switch the videos on the channel.
Are you looking for the Honda where they do all the car parts?
No, this was I was looking for. It was a Honda walking robot. So let's see.
There it is, right there. Second video.
Oh, the Honda one.
So I guess they changed it up on me.
Stalker.
Dude, I didn't know they got tape.
Maybe it was this one. I think it was this one.
Is it the space thing?
Fast forward.
Full speed.
Or fast forward.
Running around. Well done.
Notice it's balancing on its own.
A bicycle.
Also notice it moves sideways too.
Who's controlling that? Labor.
Making America fat.
Yeah, I wouldn't be able to be used in America. We're all
I would walk anywhere.
Said the student looking at the professor. Thanks. But just think about.
Planning around.
Notice it's going sideways.
You just use it.
What? They're talking no subtitles.
Now here's the question: is this a robot?
No.
Yes.
No, it's controlled by the
No, it's not a
person.
sensor. The sensor
There's
is
sensors, but it's still. It's basically Swedish wheels, yeah.
So this is a powered Swedish wheel. So it'll go forward powered and it'll go sideways powered.
That's unbelievable.
That much.
That's cooler than the Make money on that.
How much does this cost?
More than your house.
Priceless. I can almost
They couldn't
assure
even
you that
afford to
it's
have
not
a car.
available yet.
Probably a lot.
How fast does that thing go? Is it that slow? Or is it like?
Might as well just walk.
What do you get to stop?
You're gonna be like in the bar. Why stand up? Like why dance? Just ride this thing around.
Yeah, really.
Yeah, you want trip?
Yeah.
Perfect.
It's hard to get like a.
Oh, it's terrible. That's got my beat out this time.
Obviously, you guys are pretty impressed with this, right?
Dr. Conrad, have
Yes.
you seen the Romola video from Ted? They got the three-legged thing? that walks.
The
It's all about
Robotic.
locomotion, if you want to pull it up.
You eat a cheeseburger in this?
All right, so yeah, can you eat a cheeseburger while you're riding?
From the driver. Can you order 50 pounds of
And it's gonna be like that commercial, Subway commercial where
Does fryer grease make it slip?
Waterproof.
All right, so that is the start of our discussion on locomotion. In other words, in our book, chapter number 2 takes a look at locomotion. We've already discussed this in class. Legs, wheels, aerial. What's missing? Underwater, slithering, climbing, treads, hopping, or are some of these just extensions of the other ones? So legs, hopping, that would be one leg, right? Slithering, that would be like, I don't know, no legs.
That'd just be a bunch of wheels.
Or a bunch of wheels. You never know. Climbing, that almost sounds like legs / arms. Treads, that kind of sounds like wheels. So what we're going to do is we're going to take a quick 5-minute break, and then we will come back and go to the rest of the lecture with some time at the end to take a look at Labview. All right? Thank you. If you could hit that. All right, we're starting back up. Again, this is lecture number 2. The first start, or the first discussion, is going to be locomotion. And again, chapter number 2 goes into great detail about different types of locomotion. And one of the examples, or what he shows in the book, are, if you think about in nature, what are the different types of motion that happen. One is hydraulic, flow in a channel, eddies, things like that. Crawling depends on frictional forces. Sliding or slithering also depends on frictional forces. And running is, if you want to represent it with the basic kinematics of motion, looks very much like a multi-link pendulum. If you think about all the different joints on a leg. If you have jumping, again, it is similar to a multi-link pendulum with oscillatory movement. And then simple walking, your resistance is to motion is gravitational forces, because with a true walk, it looks more like the rolling of a polygon, and if you make the steps small enough, it actually looks like a sphere. But if you look at all of these different forces in nature, what's one set of locomotion that you don't see?
Flying?
Well, flying is one of those that we're not showing here.
Propellers or something.
Propellers or something like that. And what else?
Magnets.
Magnetics.
What's the major one?
Wheels.
Wheels.
Yeah.
Obviously, wheels aren't natural in nature. Otherwise, you'd be seeing Rosie the Robot-like creatures in the world. So one thing I want to take a look at right now is let's look at a little bit of detail on legged locomotion. And in particular, let's take a look at staccato. Now, I've passed around a staccato to several people to look at. There's one up here on the screen, and
You broke it.
I'll show you one up close in the dock cam. If we look really closely, we've talked about this before. We have a battery source, or our power source. And if we look a little bit closer, we have several parts of lasting social value. One of them right here is what's called a Darlington transistor array. What do you think that's for?
Control.
It's for control. And if we look at how this leg motion works, you'll understand why we use a Darlington transistor array. Another thing that we have on board, which I don't think you could tell what the number is, it is not easily readable.
There you go.
It is a device called an MSP 430 microcontroller from Texas Instruments. What we have is a microprocessor brain and a transistor that will actually help move the legs. That is our simple control, so we're not using pneumatics. Then if we look at the actual locomotion, what makes it move? We have this very, very, very fine wire right here, which is called muscle wire or nitinol or flexinol. It is a nickel titanium alloy that when you heat it, it contracts. And when you cool it, as long as there's an opposing force, it'll go back to its original length. What usually happens when you heat a metal? It expands. But in this case, this metal changes it deforms into a more ordered crystalline structure and actually contracts. So what does that mean? Well, that means that we have a leg here that works like a muscle, or it has a muscle to allow it to move. So let's take a look at general concepts of legs. If you think about your typical leg, and I'm talking about let's even look at an insect. That's a simple way to start. By the way, how many legs in an insect?
6
legs. 6 legs?
Really?
I thought they had 8.
6
or more.
All right, insects have 6. Arachnids, spiders, they have 8. So an arachnid is not an insect.
Not a robot.
And it's not a robot either.
Indeed.
So in our orientation, we have a insect body. We'll call this Taquito, right? And it has 6 legs. Now, how do you think these 6 legs are going to actually maintain its stability? How many legs do you need on the ground at any one time to always ensure stability?
3.
3, right? But humans, we have 2. How can we stay stable all the time?
Big toes.
How cool we are.
So the question is, or the answer is,
Negative feedback.
we don't stay stable all the time, do we?
No.
So if you have 3 legs, you're always assured of being stable unless you have an unbelievable force which can push you over. But with 2 legs, we stay because we have a feedback system associated with balance, the inner ear, muscles that will keep you upright. So in this case, to always be assured that we're on the ground, we're going to have 3 legs on the ground. And it probably is worthwhile to say that it's the same legs, right? So it's going to be this one, this pair, or I should say those 3. And then maybe you could have these 3 on the ground. Does that make sense?
Yep.
So if I want to walk, what do we have to do with these legs?
3 stay still, 2 or 3 move up.
We have to move them how?
Consecutive.
At the very least, we need to move them forward and back,
Sequence.
right?
Yeah.
But when you walk, are you always shuffling and legs always on the ground?
No.
So usually it would be helpful to raise as well. Would you agree?
Yes.
So now we have motion forward and back,
Open.
And we have motion up and down. I'll represent this as up and down. Which means these are what we call degrees of freedom. So each leg has how many degrees of freedom?
2.
2. Forward and back, up and down. And each leg has that. So we have 6 times 2. So our robot kind of has 12 degrees of freedom, which means you can have up to, if you want to control each one separately, it's going to have a really astronomical number of possibilities of motion for all the legs. But only some of them are going to be worthwhile, right? So, if we said that we don't want to drag the feet on the ground, and we said that we want to have 3 on the ground at any time to keep stability, let's think about how we're going to create a gate, or what we mean as a way to allow it to walk. So in my slides, I said, let's take a look at a video of the Stalker controlled, considering the gate and the control of these gates. So the video is not that good, so it's not going to get any better than this. And you've seen this already, and the response to somebody was, go ahead, the smarmy remark was, it's so slow. These muscles actually don't work all that good. They require an awful lot of energy. Now, are you noticing the legs are going up and down, and they're going forward and backwards? Kind of hard to see. I'm glad some bad-looking video didn't pop up. I can look at this one too.
Top right looks so good.
I've seen this one.
Yeah, shoes.
This is a really old video. This is at least 10 years old, probably even older. No, this is 13 years old, so it's a bad camera. Notice that this is also lifting its legs. Interesting enough, for the feet, I put on pencil erasers because it grabbed it a lot better. Ooh, that looks cool, robot snake. Squirrel? All right, where was I? So, what I want you to do is to think about what are the sequences of moving legs that will make this work better. All right? Keep in mind that we said our motion is going to be forward and backward. And up and down. So what I would like you to do is to, with somebody who's sitting near you, solve my walking problem. Should I give you a hint?
Yes.
All right. Step number 1. I bet you, as we currently are there. Well, I tell you what. Let me make this a little bit easier. So we have Stalker, and we have some legs. And if we look at this from the side, we have the legs that look like this. You will have some wire. I should use a different color. You will have some wire that attach here for each leg. And then you will have some wire that will attach like this. Now, to make things a little bit easier, we'll make one picture. We'll just show this like this, even though it's going to be taught. So with the up and down, And with the forward and back, you will actually have two sets of legs. You'll have the A set, and you'll have the B set. Remember, we said this would work best if we worked in tripods. So obviously to walk, you're going to need to be lifting legs and moving them forward and back, or back as we say it. So our action will be pull back. That will be activating, and then our activation will be to pull up. So I'm going to say, you know, I bet that the way this to work good is our step number 1. I'm going to want to lift some legs. So I will say, lift the B legs. Does that make sense? So now we're getting the B legs out of the way.
What?
Does that make sense? And I bet you my next step, number 2, will be to pull the A legs back. So now tell me what 3, 4, 5, etc. will be. And so what I'll do is I'll have one of you present this to me for a trip to the prize closet. All right. Say that again?
Did we get the broken dog?
You get the broken dog? Oh, maybe not. So, spend a couple of minutes talking between each other, and we'll pause. If you could turn that off. All right, we have, most of us have done this. Would you like to come up and make the presentation? Bring your sheet of paper. And if you say it to the class, you need to do it. You need to be loud.
Okay.
Yes. So speak to the camera.
That's what I did. Yeah.
First, you have to lift B up. Then you move A back and B forward. Those steps are interchangeable.
Also, you're saying that maybe you could do this at the same time?
Yep. And then you do B down, A up, and then forward and B back. Those are also interchangeable. And then you put A down, and it's looped.
All right. So the important thing to take a look at is that when A is going back and B is going forward, the aspect of that is
moving forward.
They can be done at the same time because B's already in the air. So that answers your question back there, saying, can't you do that? Yeah, the answer is yes. And then the other one you said could be done in parallel is, which one was that?
6 and 7.
4, 6 and 7. Since A is already up in the air, it could go forward at that point. All right, I'll live with that. That sounds good. You can take that with you. And you get a trip to the prize closet right after this, including an opportunity to get the hose.
It's gonna treat you like his hose.
Let's see how well I can.
So when I solved this, I came up with this. Let's see. Oh, FB saying forward, back, up, down. What this meant is when I was doing this. When I was doing this, I was keeping in mind how long it's going to take, and this is for the Stakito legs to work, how long it was going to take, and how much energy I have to consume. Because imagine this, when you're running a robot, anytime you're running the actuators, it's going to draw power. So at any one time, am I drawing more than 1 unit of energy? Now let's see.
Step 2.
In one case, by the way, the energy that I'm showing up here is amps. So these little wires are drawing 1/2 of an amp for each leg. I'm sorry, for all 3 legs together.
Oh.
You get that out of 2 double batteries.
And 2 AA batteries will last 10 to 15 minutes, if you're lucky. All right. So as you're walking, you can imagine it would be to your advantage to limit the amount of time that you are contracting one of these muscles, because it just draws so much energy. So in this case, yeah, there are 3 times where I'm drawing an amp. There are 4 times where I'm drawing half an amp, and then there's 1 time where everything is resting. So yeah, it's not all that fun. Is there a better process for walking that saves energy? Well, one way that we came up with this is, if you look at the bottom of the foot, what we did is we kind of curved the foot a little bit so it would dig in, and it would literally drag the legs forward. But when it would move back, it would catch the surface. Obviously, if you have something really smooth, it's not going to work. If you have something really really coarse, like carpeting, that won't work either. If you have something like paper, actually sandpaper works pretty good too. It would walk on that. In that case, you're only using these, you're only contracting 3 at a time, and you'll never go above the half amp, and you'll draw about half as much current, but you'll have all that friction. You probably won't go as fast. But that's some of the concepts that you're going to have that are associated with legs, because it takes a lot of energy to move legs slowly. Now that's why they're coming up with a lot of algorithms that mimic biology. Think of a cheetah. A cheetah runs pretty darn fast, right? Supposedly 60 miles an hour. And they have done investigations on cheetah running, and they are identifying that the cheetah never really pounds on the ground. It is actually just using its muscles to move its leg forward and just give it a very
subtle touch,
light tap on the ground to keep its body up, but it's expending most of its energy for going forward. And so by looking at some of the models of nature, we can build better vehicles, better robots. So let's take a look at another set of legs. And that is, we kind of looked at the Asimo, and these were developed over approximately 3 years, where they got better and better and better. And oh, by the way, there's also a Sony robot called the Qdio, which is about this big from the table, and it will, it's an entertainment robot. They really haven't come out with that, but there are a couple other humanoid entertainment robots. The important thing is to keep in mind is that 2 legs, you have to worry more about balance. Notice that all of these have knees that at this point are a little bit bent, because it's easier to keep your balance when you have a little bit of bend in the knees and the legs. Let's see, is that the last picture I have? Nope. The other thing I wanted to show is to look at a little bit more detail would be a 4-legged toy robot, and this is a iCybe. This came out, I don't know, 10 years ago or so. This was designed by, I'm trying to remember who designed this. I can't remember if it was Silverlit or Wowie Toys, but this is a cheap AIBO. The AIBO came out, it was AIBO, is a Sony dog robot, it's in your book. That came out, it was anywhere between $1,100 and $1,300. This came out for $200. The unfortunate thing is, they didn't sell too well. So at $200, not too many people bought it. Right after Christmas, one year, I bought it for about $100. And 2 weeks later, they were selling them in Aldi's for $40. For those of you not familiar with Aldi's, Aldi's is a cut-rate grocery store that every so often will sell the most strangest things you've ever imagined, and they sold these things. If we were to take a look at how many degrees of freedom are on this, we have, for each leg, we have this motor, which goes up and down. We have a motor in the body, which goes forward and backward. We have, at this point right here, another motor, which moves this knee forward and back. So how many degrees of freedom do, by the way, and this has a foot that has no motor, it's just, it just moves a little bit, so it's not really considered a motorized. So this has how many degrees of freedom each leg? 3. So a total of 12 for all of them, 4 legs. Add on top of this, even though it's not really used for locomotion, its tail will wag up and down. By the way, this thing I don't think is going to work because I didn't charge the battery before I came here. Oh, this was sold by Tiger. And it's got a big battery. I wonder, oh, just for grins, let's see if it, nah, this wouldn't have any battery left in it. Let's see. Nope. Nope. All right, so also its head will go up and down. It'll go back and forth. And I think that's about it for the locomotion. By the way, if you're really interested in this, there's also infrared sensor in the front. There's a touch sensor on its nose. You can scold it. It's kind of funny. I think there's only LEDs in here. By the way, it's got a button on the top. You could pat it. If it's good, you could pat its head. It's got a sensor on the back. You could pat it, and it's good. I think this is just the power switch. And if I can try and get it to run, I'll try and make this run in the next class. But I guess it's worthwhile to see what it looks like inside, right? So I was looking for the legs, and I couldn't find them. This is the main processor for this, and they did something a little bit ingenious. They created a removable ROM so that you can program a personality for your robot and move the personality from one robot to another. But this also has it has speakers, it has other sensors. But one of the biggest problems with this, it's got wires everywhere. And this thing is not really made all that well because they've got all this stuff all over the place, which makes it a little bit hard to manufacture because it's got so many connectors. If you can see all these. In fact, I'll show this on the video screen. So some of the technology on this, you can also, I'm trying to see where this is. I believe these are memory devices, but I am not all that sure on this right here. And here's one of the more interesting parts. That, a glob of goo. What does a glob of goo usually do?
Thanks.
In some manufacturing, what they do is they put a raw chip on the board. They put wire connections to other things on it, and then they put this big glob of black goo. This most likely has the program for the robot, and they do that so that people can't pull the programming off of that and copy it and make clones of this device. And in fact, it's a very inexpensive way to manufacture. If you were to look inside your digital watch, it most likely has a very small chip in the middle with some wire bonding coming off, with a big glob of epoxy. It's not in a plastic chip. So if you look at your typical chips here, You know, it's a regular plastic chip that has inside of it a piece of silicon with connections to the outside world. This is just an inexpensive way of doing it because you don't do the plastic. So these are two examples of legged robots, and I also showed the legged robot associated with humans. And so the final thing I wanted to talk about was wheels, and it does not look like I'm going to get to it right now, so we will cover this in our next class. We will take a little bit of time to talk about Labview. Thank you very much.